Here, that's
I'm a particle physicist. I work at UCL, University of London. I work on the Large Hadron Collider. I don't know how many of you have heard of that, but I'm going to tell you about it. And I'm going to talk a little bit today about how and why we go about searching for the Higgs particles at the Large Hadron Collider. You can try and figure out, or do some homework to try and figure out why such large machines as the Large Hadron Collider are needed to look for Higgs particles. Okay, so I'll start off with a little bit of an introduction about particle physics, really, and kind of what we're doing. So what are we trying to understand as particle physicists? Well, basically, we're trying to understand the very fundamental building blocks of matter, what everything from me to you to the stars to this building is made up of. So actually, what we've understood to be the most fundamental building blocks of matter, and when I mean the most fundamental building, what I mean by that is the smallest building blocks of matter that can't be broken down any further as far as we know. What we understand to be the fundamental building blocks has actually changed throughout time. So back in the 1800s, it was actually thought that matter was that the fundamental building blocks were the 92 elements of the periodic table. It was thought that you couldn't break things down any further than that. It was then realised that these atoms that make up the periodic table were actually made up of different things themselves. So you've already heard a bit about this from Ryan, but we have this very dense, sort of positively charged nucleus of an atom, and then we have these fundamental particles called electrons sort of dashing around outside the atom. We then realised that the nucleus itself is actually built up of smaller particles known as protons and neutrons. And then we realised that those protons and neutrons are actually also built up of smaller particles known as quarks. And as far as we know, that's where we are now. But as you've seen, history's shown that as technology and knowledge progresses, we realise things are smaller than we thought before. And it's kind of like a reverse of the history of the universe itself. So immediately after the Big Bang, these sort of fundamental particles were moving around on their own, and then as the universe expanded and cooled down, the particles combined together, you start to form atoms, and then the atoms combine together to form molecules, and eventually stars and planets are formed, and then eventually we are formed. Okay, so our current understanding of the universe is known as the Standard Model of Particle Physics. This is a very, very successful mathematical theory that describes these building blocks and the interactions between them. So we have these matter particles that Ryan's introduced. So we've just talked about the quarks. There are actually 6 of them. And there's also the leptons. The electron is one of them. Ryan's talked a lot about the neutrinos. And then there are also the force-carrying particles, which are responsible for the interactions between them. The most famous of which is the photon. That's responsible for transmitting light. So when you see something with your eyes, it's because a photon is coming from a source and is interacting with your eyes. That's why you see something. So basically, the Standard Model describes all of these particles, and it's been really, really successful. There has, however, for a very long time, been a kind of missing piece to this sort of successful theory. So back in the 1960s, when this theory was being developed, there's a Scottish physicist known as Peter Higgs, who was working on the theory, and he was sort of doing some calculations, working on his blackboard and saying, things are working, everything sort of seems to work so well. The only problem is, when I try and calculate something like what's the probability of 2 particles interacting with each other, I get the answer that I get is infinity for everything that I try and calculate. And the only way I can get rid of that is if I say that particles don't have any mass. But I know particles have mass. I've got mass. He had mass. We're all massive. But if we say that particles can have mass, that means that he was getting these nonsense answers in his calculations, which obviously doesn't really make sense. So, in order to solve this problem, he actually invented a mathematical trick that allowed the theory to work, but allowed the particles to have mass and got rid of the infinities. So really it was just a trick. He was just playing around, trying to make things work mathematically. And he made this trick. And the only sort of problem with it was that it out-popped, if this trick was to be true, out-popped the existence of a new particle that we'd never seen before. So if it was true, there was a new particle had to exist, and it was a heavy particle, but we hadn't seen it. And so because everything else was working so well and everyone wanted it to really work, we started searching for the Higgs particle, also known sometimes as the God particle. So how do you go about searching for a particle that you don't even know whether it exists or not? Well, as I said, it's a heavy particle, and it turns out if you want to create a heavy particle, then you need a lot of energy. And this comes from Einstein's very famous equation, energy equals mass times the speed of light squared. So for a very massive or very heavy particle, we need a lot of energy. So what we do is we make particles that we know about, we make them interact, and we do that at very high energy, so that we have a lot of energy, which means that we're able to make particles with a lot of mass. So now I'm introducing the Large Hadron Collider, which is basically enabling us to do exactly that. It's a particle accelerator. It's basically a huge ring underground that sort of straddles the Swiss-Franco border, so it's in Switzerland and France. And what it does is it accelerates protons. Protons are those particles I mentioned at the beginning that are inside the nucleus of atoms. They themselves are made of quarks. But it accelerates protons in both directions around the ring at very, very fast, almost the speed of light. And then they're sort of moving around but sort of avoiding each other most of the time. And then at 4 points around the ring, they're focused onto each other to collide. And when they collide with each other at very high energies, they interact with each other and a whole load of new particles is produced. And what we do is we surround this collision point. This is kind of a picture here showing you've got the two proton beams coming in from here or here. And then you surround the collision points by what we call particle detectors. And basically a particle detector, this is the example of the one that I work on called Atlas. It acts like a huge digital camera. So the protons interact in the centre here, they break up and a whole lot of new particles get created. And they just literally pass through the detector. This is a huge detector. This you can see here is a human scale. So it's really big. So the particles move through, they literally interact with the material of the detector. That allows us to know that they're there. We can interpret what type of particles they are, and we can measure their momentum and their energy. And we kind of take a snapshot of it, and then next time the protons collide and they do it again, we take another snapshot, and then we save it all and we analyse it. So just to give you some numbers to understand a little bit, the protons themselves that are going around and colliding, they collide 40 million times every second. Now that's a lot, right? So we've actually got a lot of data here that we're trying to take pictures of and to store. Although we don't actually keep it all, we have to decide which ones we think are interesting. But when you're trying to produce something that's rare and heavy, like the Higgs particle, it actually only happens about once in every 10 billion proton-proton collisions. Now I think that's pretty unlikely to happen. So how do you get around that? Well, you make them collide often. So we have them 40 million times a second, and we run for a long time. So we just collect more and more data, and we say, well, it's very rare, but we'll collect so much that we will actually find some. So the challenge is to collect enough of this data and store it, and then to find the needle that is this Higgs particle amongst the haystack of all the other things that are being produced. So when these protons interact, 1 in every 10 billion is a Higgs, but the rest of the time it's something else. So we're trying to dig through all those something else's and find the Higgs. So what do we actually see in our particle detectors when we produce a Higgs? Well, actually we don't directly see the Higgs. The Higgs itself doesn't move through the particle detector. The Higgs almost instantaneously decays to other particles. And it's actually those other particles that we see in the detector. So it is possible for the Higgs, for example, to decay to 2 photons, the photons that I talked about earlier, that interact with your eyes, those ones. So actually what we would see is the Higgs, actually what we would see would be the 2 photons, not the Higgs directly. This is kind of a picture of 2 photons moving through the detector. So we've got 2 very high energy photons going in opposite directions here through the detector. That's what we see, and then we say, okay, we've seen 2 photons, maybe they came from a Higgs. Okay, so now I'm going to get quite technical, so bear with me here, but I'm going to show you sort of how we actually go about looking for the Higgs when it decays to these 2 photons. So this is just a simulation, this is not actually our real data, I'll show you that on the next slide. But basically you have these two photons produced. It's actually possible to produce two photons in other ways that isn't from the Higgs. But what you can do is you can measure their energies, their momentum, the momentum of the photons, and you can actually, from that information, reconstruct the mass of the particle that decayed into them. Okay, so if the Higgs decays into two photons, and you reconstruct its mass, you will see a cluster of them. So what I'm showing here is the number of times you get these two photons as a function of the mass of the particle that decayed into them. So the blue thing here is just any other way of producing two photons, and it just sort of steeply falls as you get to higher masses. Now, if you produce a Higgs at a certain mass, which is the mass of that particle, then you have a kind of excess of these events where you have two photons just clustering at that one place. So this is exactly what we look for. We make a plot like this, the number of times you see the two photons as a function of the mass, and you look for a little bump appearing at a certain mass, and you say, okay, I can see that bump, that means there's a Higgs particle there, or something that looks just like a Higgs particle, and this is the mass of that Higgs particle. So now I'm going to show you what we did actually see in the announcement. There was an announcement made on the 4th of July of this year, and this is what we saw. So these are two plots because there are two independent detectors looking for the same thing. So this is the two independent detectors. And so this is the real data now. You see that the sort of dots that are jumping about, that's the real data that we're plotting. And you can see the general features are the same as what I showed before. It's kind of generally falling down as you go to high masses. This is all the other types of ways that you can produce two photons. But if you look here, if you squint, you can see there starts to be a little excess of these guys where there's two photons at a certain mass here. And you can see actually in the other detector that you can also see a little excess in pretty much the same place. Because this is what tells us that we have seen a new particle with a certain mass emerging in our data. Now, Peter Higgs was actually there at CERN in Switzerland when we sort of made this announcement, and you can see him here in the audience having a little cry. And I don't blame him, because just remember, it was in the 1960s, he came up with the possibility that a particle like the Higgs particle could exist just because he was trying to sort of fix these mathematical calculations that weren't working. And 50 years later, it starts to appear in our data, and it's pretty amazing stuff. Okay, so what now? We're not just all drinking champagne, every day now that we've sort of made this discovery. We've seen something that looks like it could be consistent with the Higgs particle that Peter Higgs predicted. However, we have to measure its properties and make sure that it really is that particle. So we're busy sort of looking at that particle and seeing how it behaves. And also the LHC was not just built to find the Higgs, whatever you may have heard. We're also looking for lots of other types of particles. We're having a shutdown soon, and then we're going to upgrade to a higher energy and search again for many new particles. Okay, so that's it from me. Next, we're going to have an artistic interpretation, and in particular, there's going to be a connection with the Higgs particle, which, as I said, is in a sense it sort of solved the fact that particles couldn't have mass. It gives mass to particles, and it's the mass of objects that means that they interact via the gravitational force. So we're going to have an artistic interpretation that's going to take that into account. Thank you very much.